Hello and welcome to another episode of Math-221. Today we're going to go over section 7.1 and section 7.2. I think we probably won't get through all of section 7.2, but I'll just go up to the hour and 5-minute mark and then we'll put the rest onto next time's lecture. Okay, so let's get started with section 7.1. This is functions defined on general sets. So the topic of functions is really important and fundamental to all of math and computer science, so this is a really important section to understand. Okay, so first of all, we have the definition of a whole bunch of different things. So let's just go through all of these different definitions here and let's talk about them. So firstly, a function f from a set x to a set y. It's denoted in formal higher math in this fashion right here. So you have f colon, and then you put the name of the domain, and then you have a little arrow, and then you put what is called the codomain. So what that is, what a function is first of all, it's a relation. And so I don't know how well you guys recall relations. We did them back in chapter 1. But a relation is just a subset of the Cartesian product of x and y. So in other words, it's ordered pairs. Okay, so it's a relation from x, which is called the domain, to y, which is called the codomain, that satisfies two properties. So you must satisfy these properties to be a function. So the first one is every element in x is related to some element in y. So in other words, every element in the domain must have some element in the codomain that goes with it. And then secondly, no element in x is related to more than one element in y. So this is part of the definition of function that I expect you already knew from a previous class. So for every input in the domain, you can only have one output. So no input can have more than one output. Okay, so in other words, given any element x, little x in big X, there is a unique element in big Y that is related to little x by f. So if we call this element y, then we can say that f sends x to y, or f maps x to y, and we can write it in these different ways here. So we can write x arrow y with the f over the little arrow. I would usually read that as x is mapped to y by f, or you can write it like this, and I would read this one as f maps x to y. So the unique element to which f sends x is denoted like this, f of x, and that's pronounced as either f of x, or the output of f for the input x, or the value of f at x, or, and this is the last one that would be new to you, the image of x under f. So the set of all values of f taken together is called the range of f. I think you already knew that one, I hope. But the range of f can also be called the image of x under f. So it's the image of the domain under the function. And if you want to write that symbolically, we can say that the range of f, which is also said to be the image of x under f, we can write that in set builder notation. It's all the little y's in big Y, such that little y equals f of x for some little x in big X. Okay, so it's all the outputs that you get from the inputs that are in the domain. That's the range. Okay, and a few more terminologies down here. So given an element little y in big Y, there may exist elements in big X with little y as their image. Okay, so there may be some elements in big X that have y as their image, or there may not be any. But if you do have that f of x equals y, then x is called the pre-image of y, or it's called the inverse image of y under the function. So the set of all inverse images of y is called the inverse image of y. So if you take together all the little x's that give you y as an output, that is the inverse image of y. So symbolically, the inverse image of y is the set of all little x in big X, such that f of little x equals little y. Okay, so that was a lot of definitions. Let's go ahead and try to apply them and practice with them a little bit. Okay, so before we do that, just a word of caution about notation. So sometimes this notation here, f of x, that is pretty commonly throughout math used to refer to two completely different things. So it's used to refer to both the value of f at x and to the function f itself, and those are really different types of objects, because one is a number and one is a function. So we're going to try to avoid any confusion over what we mean by f of x by using f of x to only refer to the value of f at x, and we'll refer to the function only as f. So we'll never say f of x to mean a function. If we want to refer to the function, we'll just call it by its letter, by f or g or h or whatever it is. Okay, so now let's do some examples. Okay, so first let's talk about arrow diagrams. So an arrow diagram is a really nice and simple way of illustrating a function when there's only a small number of things in the domain and the codomain. So let's look at this one here. We have a function f from capital X to capital Y, and we've drawn an arrow diagram to indicate what are the inputs and the outputs. So in this example, for example, f of x1 is, so we just follow the x1 arrow, and that is y3. And for another example, f of x2 is, just follow this arrow, that's y1. F of x3 is y3. And f of x4 is y4. Okay, so that's how the arrow diagram works. And if you want to check the conditions of being a function, what you would need to have is that everything in the domain has some output associated with it, and all four of those elements in the domain do have an output. And you also need that there is not more than one output for any input. So you need exactly one arrow coming out of each element in the domain, and then it will be a function. Okay, let's look at this example. So we have capital X is 1, 3, 5, and capital Y is A, B, C, D, and we have the function g from X to Y given by the arrow diagram. So let's get right into this. So part A, write the domain of G and the codomain of G. I'm just going to do it up here. So the domain of G, that's given in the problem itself. So the domain is the set containing 1, 3, 5. So that's right there. And then the codomain is also given in the problem itself. So that is capital Y, which is the set containing A, B, C, D. So that's right there. Alrighty. So part B, find G of 1, G of 3, and G of 5. So all you have to do is just follow the arrows from those elements. So from 1 it goes to B. From 3 the arrow goes to also B. And then from 5 the arrow goes to, again it goes to B. Okay, so part C, what is the range of G? So this is not the same as a codomain. The range is going to be only those outputs that you actually got when you plugged in some of the inputs, or when you plugged in any of the inputs. So the range of G is going to be just B, the set containing B. Okay, because that's the only output that we get. All right, part D, is 3 an inverse image of A? So what that's really asking is there an arrow from 3 to A? Or if you follow an arrow back from A, will it lead you back to 3? So the answer there is no. 3 is not an inverse image of A. On the other hand, 1 is an inverse image of B. Because there's an arrow that would lead you back from B to A, or sorry, from B to 1. Okay, so 1 does map to B, that means 1 is an inverse image of B. Okay, part E, what is the inverse image of B? So the inverse image of B is going to be everything that maps to B, so all of the inputs that would give you B as an output. So the inverse image of B is going to be all 3 of those elements, 1, 3, and 5, that map to B. And then the inverse image of C There's nothing that maps to C, so that's going to be the empty set. Okay, and then finally part F, represent G as a set of ordered pairs. So here you're just making a list of all the inputs and the outputs as an ordered pair. So we have 1 goes to B, we have 3 goes to B, and then we have 5 goes to B. So this is how you could represent the function as a set of ordered pairs. Okay. Okay, everybody, here's your homework problem. It's extremely similar to the one that I just did. So go ahead and give it a try, and then check your answer in the back of the textbook. Okay, so now we're going to go through some different examples of important and kind of classic or interesting functions. So the first one here is an identity function. So an identity function is one where the input is always the same as the output. That's what is meant by an identity function. So input equals output. And so in this particular case, we're calling IZ the identity function defined on the set of all integers. So this down here, this is integers. So they're just using that subscript as a way of letting you know what set the identity function is defined on. Okay, and we're supposing that E, B sub I to the jk, k of t, and u sub kj all represent integers. And they want us to find the value of the identity function for all of these. This is so easy. All you do is just say the input is the same as the output. So these are just the same as the output. Okay, so identity function, it just returns whatever you put into it. Input equals output. Okay, go ahead and finish up with A and B there. Okay, so now let's look at another example. So in this one, what I want you to see is that sequences themselves are actually functions. So you can take a sequence and write it as a function. Okay, so this one is saying find functions defined on the set of non-negative integers that define the sequences whose first 6 terms are given below. Okay, so what I'm basically trying to do is to write a formula that would give me these values of the sequence as an output. Okay, so I think what I'm going to do, so it depends on where you want to start your subscript at, but I think what I'm going to do is, so for part B here, I'm going to say that A sub 0 is the first term in the sequence, and then I'll say that A1 is the second one, and then A2 is the third one, and then A3 is the fourth one, and so on. So I decided to start with A sub 0 because I think that'll make it easier for me, but you could have started with A sub 1 or really anywhere you want to. Okay, so I think what I'm seeing here is that each time I'm doubling the subscript, so like here I have 0, and this is 0 times 2, and this is 1, and then 2 times 1 is 2, and then I have 2, and 2 times 2 is 4. So every time here I'm doubling the subscript. So that's certainly going to be part of my formula, is that doubling thing. But then the other part of it is dealing with the negative. So every other term is negative. So I need to deal with this alternating negative. So we talked previously about how to deal with that, how to write a formula that deals with that. So your choices basically are, I'm going to call my general formula A sub I. So I can either do 2 times I times negative 1 to the I, or I could write it like this, 2 times I times negative 1 to the I plus 1. So those will both give me an alternating positive negative pattern. They'll just be one off from each other, so I need to just figure out which one of these is the correct one. So this first one, if I plug in I equals 0, that would give me 2 times, well actually they would both give me 0, wouldn't they? I better plug in a different number. Let me see, eraser, let me try plugging in 1. And, okay, so I times 1 from that first formula, that would give me 2 times 1 times negative 1 to the 1, which would be negative 2. Okay, that is the one that I want. Let me just make sure the other one doesn't work, so I show you what would happen if you had done the wrong one first. So that would have given me 2 times 1 times negative 1 to the 1 plus 1, which would have been 2 times negative 1 squared, which would be positive 2, which is not the right one. So the one that I want is this one. Okay, so that's my formula for the sequence. And now to write it as a function, all I'm going to do is just, like, let's just literally write it as a function, like in function notation. Okay, so this is the function notation for this sequence. And all you have to do is just plug in any integer into that, and it will give you what the value of the sequence term is. Okay, let's look at this next example here. So this one is a little bit interesting because the domain of the function is somewhat unusual. So the domain here is actually the power set of the set A. So do you remember what a power set is? So the script P of A thing, this is the set of all subsets of A. So that's why when you look at part A, B, C, and D down there, the thing that you're plugging in to the function f is actually a subset of A. Okay, and then the way the function is defined is also kind of interesting. So capital F is defined to be 0 if the subset that you're plugging in has an even number of elements, and then it's 1 if the subset you're plugging in has an odd number of elements. And that's all it is. So that's kind of interesting. So let me do part B and D here, and then A and C are for you. So part B, capital F of the empty set. So the empty set, how many elements does that have? That has 0 elements. So this is going to be 0. The empty set has 0 elements. Oops, I cannot. That's not even not spelling, that's just not even a letter. Okay. So the empty set has 0 elements, and 0 is even. Okay. And then part D here, so capital F of the subset containing 2, 3, 4, and 5. This is also going to be 0 because the set that we plugged in, 2, 3, 4, 5, has 4 elements. I'm just going to abbreviate elements like that, which is even. Okay, so go ahead and do part A and part C. Okay, now let's look at another function that is kind of interesting. So we're calling this set J sub 5. We're calling that the set containing 0, 1, 2, 3, and 4. And we're defining a function, capital F, from J5 to 2J5 as follows. So for each x in J5, f of x is defined to be x cubed plus 2x plus 4 mod 5. And remember what that mod 5 thing is? That is the remainder that you get if you do long division by 5. Okay? So let's do C, D, and E here, and let's see what we get. So C, we're plugging in f of 2. So this is going to be 2 cubed plus 2 times 2 plus 4 mod 5. Okay, so now I'm just going to simplify. So this is going to be 8 plus 4 plus 4 mod 5. Okay, 8 plus 4 is 16. So this is 16 mod 5. And if you do long division by 5, you will get a remainder of 1 from that. Okay, and if you want to do that in your head, you can just kind of realize that 16 is 1 more than a multiple of 5. So the nearest multiple of 5 that's below 16, that's 15, and then you would need to have a remainder of 1 to get up to 16. Or you can just do the long division, just do a little like this. You get 3, 15, subtract, and then you get 1. So that is 16 mod 5. Okay, so part D, capital F of 3, we're just going to do the same thing. So this is 3 cubed plus 2 times 3. That is not, I mean, that is 2 times 3, but that's not what I wanted to write. Oh, my eraser has disappeared. Where does it go when it goes away? There it is. Nope. Okay. Okay, sorry about that, guys. PowerPoint is very mysterious. Okay, so 3 cubed is 27, and then this is 6 plus 4 mod 5. Okay, so this is 37 mod 5, and then again, by the same logic I was telling you before, the remainder is going to be 2, because 37 is 2 more than the nearest multiple of 5, which is 35. Okay, and then part E, plugging in 4, so we're going to have 4 cubed plus 2 times 4 plus 4 mod 5. So 4 cubed is 64 plus 8 plus 4 mod 5. So this is going to be 76 mod 5. And then that is 1 more than a multiple of 5, so this is going to be 1. Okay, so in this example what we saw is just that you can define functions in some interesting ways using other operations that we had learned from previously in the class. Alright, go ahead and do part A and part B and finish up. Okay, so let's look at this example here. This example is a little bit interesting in the sense that we have an output that is actually a set. So let D be the set of all finite subsets of positive integers, and define a function t from the positive integers. So this symbol right here, this stands for the positive integers, to D as follows. For each positive integer n, t of n equals the set of positive divisors of n. So the output that you're getting is actually a set. So let's try part D here. So t of 5. So I'm just going to list all of the positive divisors of 5 as a set, and I think there's only 1 in 5. Now you might be thinking at this point that this violates the rule on functions where you're only allowed to have 1 output for each input, but it actually doesn't, because this is still just 1 output. Because that set is like a solid object, it's like a block. Even though there's things inside of it, the set itself is just 1 object. Okay? And then in part E, so we're doing t of 18. So I'm just going to list all the positive divisors of 18. Let's see, 9, and then 18 itself, right? Is that all of them? And then F, 21. So I'm just listing the positive divisors of 21. I think that's all of them. Okay, so go ahead and finish up with A, B, and C, and check the answers in the back of the book. Okay, so here's another interesting example in the sense that our inputs are ordered pairs, and our outputs are also ordered pairs. So that is a thing that can happen. So the way that you write it when your input is an ordered pair here is you just list the elements of the ordered pair in parentheses, and you don't sort of put another set of parentheses here. That would just be like a little bit too messy looking, I guess. So you just list the two things in the ordered pair like that. Okay, and then our output here is an ordered pair, and again, that's not violating the rule about functions only having 1 output for each input, because we think of the ordered pair that we get out as being like 1 block, 1 solid object. Okay, so let's go ahead and do part C here. So capital F of 3, 2. Okay, so I'm just going to plug these into the formula. So 3 is A and 2 is B. So this is going to be 2 times 3 plus 1, comma 3 times 2 minus 2. And then I'll just simplify these. So this is going to be 7 and 4. Okay, and then for part D, we'll do the same thing. So now we have 1 for A and 5 for B. So this will be 2 times 1 plus 1, comma, 3 times 5 minus 2. And that's going to be 3 and 13. Okay, go ahead and finish up with A and B, and we'll go to the next slide. Okay, so now let's talk about function equality and functions acting on sets. So first of all, we have theorem 7.11. So this says, if capital F is a function from capital X to capital Y, and G is also a function from capital X to capital Y, then capital X equals capital G if and only if capital F of X equals capital G of X for all X, little x in big X. Okay, so in other words, two functions are the same function if and only if the value of the function is the same for every element in the domain. And they do also need to have the same domain and the same codomain. Okay, and then our second definition here is about images and inverse images of sets. So here we have little f from big X to big Y is a function, and then big A is a subset of big X, big C is a subset of big Y. And then what we can actually do is we can define this notation here where we're plugging in, we're not just plugging in an element of the domain, we're plugging in a subset of the domain, which is a little bit strange thing to do. So basically it's like plugging in more than one element at once. And then what you're going to get out from that is you're going to get out all the outputs that would have come from all of the elements in that subset that you plugged in. Okay? So we'll look at some examples of what that looks like in a second. But basically you're plugging in a bunch of elements from the domain at once, and then you're getting a bunch of outputs at once. And so that is the image of a set. And then you can also do the same thing for the inverse image. Just like we had the inverse image of single elements, you can have the inverse image of an entire set. So if C is a subset of the codomain, you can try to find the inverse image of a bunch of elements from the codomain all at once, and it'll just be the collection of all of the inverse images of each individual element that you were looking at in the codomain. Okay, so it'll be all of the little x's in big X, such that when you plug in little x, it gives you something in that set C whose inverse image you were trying to find. So f of A, that's called the image of A, and f inverse of C, that's called the inverse image of C. And now let's look at an example. Okay, everybody, let's look at this example. So number 39, let x equal 1, 2, 3, 4, and let y equal a, b, c, d, e. Define the function g from x to y as follows. G of 1 equals a, g of 2 equals a, g of 3 equals a, and g of 4 equals d. So first we just have to draw an arrow diagram, so let's go ahead and do that. So I'll let this be x, which has 1, 2, let's make that a really solid 2, 2, 3, and 4. And then we have y, which has a, b, c, d, and e. Okay, and so the arrow diagram, 1, 2, and 3 are all going to point to A. And then 4 is going to point to D. Okay, and then for part B, let me start it down here. So they've defined these three sets for us, A, C, and D, capital A, capital C, and capital D. And we're going to find some images and some inverse images of those sets. So first of all, G of A. So all we're going to do is we're just going to plug in to G all of the things that are in the capital A set. So this is going to be G of 2 and G of 3. Okay, so this is just going to be, let's see, G of 2 is A and G of 3 is also A, so this is really just going to be A. And then the second one, g of x. So we're just plugging in everything that is in x, and then we're just collecting all the results into a set. So this is g of 1, g of 2, g of 3, and g of 4. And then that's going to equal, so 3 of them give you a, and regardless of whether you write that once or whether you write it 3 times, it's the same thing. So this is just the set containing a and d. Okay, and then we have to do some inverse images. This is a little trickier. So G inverse of C, this is going to be the set containing all elements of X that have an output in C. Let me just describe it to you that way. So this is all the elements of X that have an output in C. Okay? So in other words, another way you could think of it is it's G inverse of little a, which is that element that's in C. So it's all the elements that are in the inverse image of A. So what are the elements that give A as an output? This is going to be 1, 2, and 3. So it's all the inputs that give you things in C as an output. And in the same way, G inverse of D, again, I'm just going to describe it this way. So all inputs that give, let's see, B or C as an output, because B and C is what are in capital D. Okay, so what are all the inputs that give B or C as output? Well, there aren't any. So this is just going to be empty. In other words, this is the empty set. So we encountered the empty set again unexpectedly. All right, and then G inverse of Y. So this is going to be all inputs that give A, B, C, D, or E as output. So that's actually all of them, because Y was all the possible outputs. So both 1, 2, 3, and 4, they all give outputs that are in Y. So this is going to be 1, 2, 3, and 4. Okay. So here's one for you that's really similar to the last one. So go ahead and do this one and check your answers in the back of the textbook. Okay, so now on to section 7.2, and let's see how much of this we can get through. So in this section, we're going to talk about one-to-one and onto functions, and then also about inverse functions. And again, these are 3 definitions that are really common in math and computer science, so they are important to understand. Okay, so first of all, we're going to define what it means for a function to be one-to-one. So let capital F be a function from a set X to a set Y. F is one-to-one or injective if and only if for all elements x1 and x2 in X. So here's the important part. For all elements x1 and x2 in X, if f of x1 equals f of x2, then x1 equals x2. So another way to say that, if you want to say it as the contrapositive, because it's an if-then statement, you can always form the contrapositive. Then remember, you switch the order of the if and then, and you negate each little part. So that would be if x1 does not equal x2, then f of x1 does not equal f of x2. And I think this version is the easier way to understand it. So basically what this is saying is different inputs give different outputs. That's what that means. Different inputs give different outputs. So there are a lot of functions that are not like this. Many of the examples we've looked at already had different inputs giving the same output. But if your function has the property that different inputs always give different outputs, then it is one-to-one or injective. So that's the easier version to understand. The easier version to prove is this one. So that's the one that we'll use to prove one-to-one with. because assuming that something is not equal is not a very strong assumption. It really doesn't give you much to work with. And then symbolically, they've just stated it here again at the end. Symbolically, the function f from x to y is 1 to 1 if and only if for all x1, x2 in x, if f of x1 equals f of x2, then x1 equals x2. Okay, now on the other hand, if your function is not 1 to 1, what does that mean? So if you just take the negation of the last statement, the for all statement that we just went over, if you just negate it, the for all switches to an exists. So that would mean there exist elements x1 and x2 in x with, and then the second part here, this is the negation of the if-then statement. So remember, when you negate an if-then statement, you keep the if part true and you make the then part false. So this together reads, there exist elements x1 and x2 in x with f of x1 equals f of x2 and x1 does not equal x2. So basically this is saying there are different inputs with the same output. So there are at least two inputs that are different from each other that give you the same output. So that is not 1 to 1. Okay, let's look at some examples. Okay, so first of all, an easy way to see if a function is 1 to 1 is just by looking at its arrow diagram. So if you are looking at a 1 to 1 function, what you're going to see is that each point in the domain is having an arrow that goes to a different point in the codomain. So arrows never point to the same point. Okay, and then if you're looking at a function that is not 1 to 1, you'll see that there would be at least two things in the domain that would have their arrows going to the same point. Okay, so that would not be 1 to 1. So the way you can think of this is that a 1 to 1 function separates points. It keeps them separate from each other. If you follow the arrows, your arrows stay separate. Whereas a function that is not 1 to 1, it collapses points together. So when you follow the arrows, sometimes they lead you to the same point. Okay, and now let's look at the definition of onto. So this is a property that is somewhat similar to 1 to 1, but it has a different meaning. So let f be a function from a set x to a set y. F is called onto or surjective if and only if, given any element little y in big Y, it is possible to find an element little x in big X with the property that y equals f of x. And if we want to say that symbolically, the function f from x to y is onto if and only if, for all little y in big Y, there exists little x in big X such that f of x equals y. So basically what this is saying is every possible output has some input that produces it. Every possible output, so what I mean by possible outputs is everything in the codomain. Every possible output has some input that produces that output. So basically the function reaches every possible output. The function reaches the entire codomain. Okay, and then if a function is not onto, what that means, so it's just the negation of the for all statement. So a function f from x to y is not onto if and only if there exists some little y in big Y such that for all little x in big X, f of x does not equal y. So this is saying there is some possible output, and by possible output, again, I just mean something in the codomain that can't be reached from any input. Like there's no input that will reach it. Okay, so that would not be onto. Okay, so let's look at what the arrow diagram of onto and not onto look like. So if you're looking at the arrow diagram of a function that is onto, you'll see that every point gets reached. So every point over here is reached by some arrow. And on the other hand, if you're looking at the arrow diagram of a function that is not onto, there will be some elements that are never reached in the codomain. So these are never reached. Okay. Okay, so now let's look at some examples where we talk about whether a particular function is one-to-one or onto. So we're going to start off easy with some arrow diagram examples. So let capital X equal ABC and Y equal capital Y equal WXYZ. Define functions h and k by the arrow diagrams below. Okay, so part A, is h one-to-one? Why or why not? So is h 1 to 1? Let's see, it is not. So the reason it's not is because these two arrows right here, they go to the same point. So it's no, and it's because capital H of B equals capital H of C. Okay, but B and C are different elements, so that's not supposed to happen. Okay, is it onto? H onto? So if it were onto, it would need to have every element of the codomain be reached, but they're not. So this is another no, because X and Z are never, no, that's not how you spell never. Are never reached. Okay, so that was part A. And then for part B, is K one-to-one? So let's look at K. Yes, I believe in K, every input goes to a different output. Okay, so there are no pairs of arrows that are going to the same outputs. And then the other question is K onto. So does every element in the codomain of K get reached by some arrow? No. So Z is never reached. Okay. All right, so here's another example that is extremely similar. Now, the solution for B is not in the back of the book, but I would still like you to go ahead and try both parts A and B of number 7 here. So go ahead and pause the video, try both parts, and check the answer to A in the back of the book, and then I will go over B in just a second. Okay, so I'm going to go over the solution to B because that was not in the back of the textbook. So part B is G one-to-one. So G 1-to-1. Let's look at G. No, it is not. No, because there are 3 elements that go to the same output. So G of A, B, and D are the same. Okay, and then is G onto? No, it is also not, because little g is never reached. Little g is never reached. Okay? Okay, so let's look at another homework problem here for you. So go ahead and try doing this one. So they don't have an arrow diagram, but you could certainly make one if you wanted to, or you can just look at what they've written here. Go ahead and try this one, and then check your answers in the back of the book. Okay, so now let's talk about how you can disprove or prove that something is one-to-one. So if you would like to prove that a function is one-to-one, obviously for the small examples that we just did where there were just a few elements, it's really not hard to see. But if the domain and the codomain of F are large or even infinite sets, then it is a little tricky. So if you want to prove that F is one-to-one, what you do is use the method of direct proof. So you suppose that x1 and x2 are elements of x, and then you also further suppose that f of x1 equals f of x2. So remember, let me just remind you of what the definition of one-to-one is. So it's for all x1 and x2 in the domain. It's if f of x1 equals f of x2, then x1 equals x2. So that's the definition of one-to-one. So what you're doing when you're using this proof technique is you're just saying let x1 and x2 be elements of x. That's this part here. And then you're doing direct proof, so you're assuming the if part, which is right here. So you're also assuming this f of x1 equals f of x2. And then your goal is going to be to show that x1 equals x2. Okay? And then if you want to prove that f is not one-to-one, so you're going to have to show an example that is a counterexample to this one-to-one definition. So in other words, you would need to find elements x1 and x2 in x that would make that if-then statement false. So to make the if-then statement false, you need the if part to be true, that's this, but the then part to be false. Okay, so you need that f of x1 is the same as f of x2, but x1 and x2 are not the same. So in other words, you have to find two different elements of the domain, two different inputs that give you the same output. So that is how you show it is not one-to-one. Find two different elements that give you the same output. Okay, now if you want to prove that something is onto, so let me just remind you of what the definition of onto was. So onto means that for all y's in your codomain, there exists some x in your domain such that f of x equals y. In other words, this is saying for every possible output, I can find an input such that that input gives me that output. So for every possible output y, there exists an input x such that x really does output y. So if you want to prove that f is onto, you just start off by supposing that little y is an element of big Y, so y is in the codomain. And then what you have to do is you actually have to find an element, little x, in big X. So you have to find an element in the domain that produces y as the output. And that can be kind of tricky to do. It's going to involve some scratch work, but I will show you how to do it. And then to prove that f is not onto, what you're going to need to do is you're going to find some element of the codomain that is never reached by any element in the domain. So in other words, an element little y in big Y such that little y does not equal f of x for any little x in big X. So an element of the codomain that is not the output for any possible input. Okay, so let's go ahead and do some examples. Okay, so let's look at an example here where we're going to prove or disprove that a function is one-to-one and onto. So define little g from the integers to the integers. So this symbol here, this is the integers. By a following rule, g of n equals 4n minus 5 for all integers n. So part 1, is g one-to-one? Prove or give a counterexample. Okay, so I think that little g is one-to-one, and the reason I think that is because the formula here is a line. So g, if we would graph it, it would just be a line, and on a line, every input has a different output, unless the line is horizontal, but this is not a horizontal line. So yes, I do think it's one-to-one, and I'm going to prove that. So let's go through the steps of the proof. So the basic technique is to suppose that x1 and x2, so I'm just following from up here, suppose x1 and x2, sorry, that's like the biggest highlighter, or sorry, the biggest comma of all time. Okay, so suppose x1 and x2, so they're not going to be elements of x in this case is z, so x1 and x2 are elements of z, and then I'm just going to keep copying from up there such that f of, oops, it's actually not f, is it? It's actually g. So So such that g of x1 equals g of x2. Okay, so now what I'm going to try to do is to show that we will show that x1 equals x2. So that's our goal. And I'm putting that in brackets to show you that that is an optional statement. You can put that in your proof or take it out, whatever you like. Okay, so what do we get from our supposition here? We know that x1 and x2 are integers, and we know that g of x1 equals g of x2. So I'm going to use the fact that g of x1 equals g of x2 because I know the formula for g. So that means that 4 times x1 minus 5 equals 4 times x2 minus 5. Okay, so can I go on from there? Can I just keep simplifying from there? So I think if I add 5 to both sides, I get that 4x1 equals 4x2. And then if I cancel a 4 on both sides, I get that x1 equals x2. Okay, so I got that x1 equals x2, so g is 1, 2, 1. Okay, so that wasn't too bad. And that's really all you have to do. You just take two elements from the domain, suppose that when you plug them into the function they're the same, and then actually use the formula of the function, and try to use that to simplify down to just having that the two elements in the domain were equal. Okay, so let's go over the second part here, whether or not G is onto. So you might be tempted to say that G is onto because you know that G is the formula for a line, and lines should cover all possible outputs. Like if we just graph a line here, like every real number along this y-axis here would be reached by some input. But this would be what it would be like if you were going from the reals to the reals, and in this case we're going from the integers to the integers. So in this situation our line is not so much a line as it is like a series of points. So there can be some inputs here that were, or sorry, some outputs here that we're missing. And that is actually what's happening here. So because we're only putting in integers, we're going to be missing some possible outputs. Okay. So let me give you a little proof here. So part 2, G is not onto because so you have to think of something that you actually missed in the codomain that you never got as an output. And the key here is that you're missing everything that can't be written in this form of 4n minus 5, where n is some integer. So, for example, things that are divisible by 4 would never be able to be written that way, because you can't write something that's divisible by 4 as 4n minus 5. That minus 5 part would take you off of being a multiple of 4. Okay, so just for example, 4 is never an output. Okay, so I'm going to say it like this. There is no n in Z such that G of n equals 4. And then I'm just going to write a little proof of that statement. Okay, so I'm going to do it by contradiction. So suppose there is some integer n such that G of n equals 4. So if that were true, if there were some integer n such that G of n equals 4, then 4n minus 5 would equal 4. So I'm just plugging in n into G. Then we could add 5 to both sides to get 4n equals 9. And then I could divide both sides by 4 to get n equals 9 over 4. But 9 over 4 is not an integer. Okay, 9 over 4 is not an integer, so n cannot equal 9 over 4 because n was supposed to be an integer. So this is a contradiction. So that means our supposition was wrong. So g of n does not equal 4 for any n in Z. Now, do you guys see what I've done here? I've done exactly what is written up here in this box. I found an element in the codomain such that that element does not equal g of n for any n in Z. Okay, so g is not onto. So that's what you have to do when you're trying to prove that a function is not onto. You've got to find something in the codomain that is never reached and then prove that it's never reached. And to prove that it's never reached, usually the easiest way to do is by a contradiction. Suppose that it is reached, then show that leads to a contradiction. Okay, so let's look at another example here where I am going to prove that something is onto. So here we have another formula where it's just a line, but because we're going from the reals to the reals, this function is onto. So I'm going to prove that it's onto. Okay, so yes, this is onto, and let me write a proof. So I'm just going to follow the outline that's up here. So suppose that little y is any element of big Y, and in this case my big Y is the real numbers. So I'm going to suppose little y is in the real numbers. And now what I'm going to show is we will show there is x in the real numbers. So remember, big X is R. I think this is a typo right here. This is supposed to be a little x. Okay, so we will show there is a little x in R with, so it's not f of x, it's g of x equals y. Okay, so at this point you need to do some scratch work, and this scratch work is not part of your proof. So I'm going to put my scratch work in like a little bubble over here, like a little cloud, just to show that it's not in my proof. So this is scratch work. So what you've got to do is actually solve for what x would be in order to find it. So what would x have to be? Okay, so remember, we're trying to find x in the real numbers such that g of x equals y. So here's what we've got so far. We want g of x equals y. So g of x is 2 minus 3x. Okay, so now what you've got to do is just solve for x. Okay, so I am going to subtract 2 from both sides of this equation. And then I'm going to divide both sides by -3. Okay, so that gives me x equals y minus 2 over -3. Okay, so this is what x would have to be in order to produce y. But again, this is scratch work. So this is my scratch work cloud. Okay. So back to my proof. So I supposed that little y was an element of the reals, and then my goal is to show that there is some element x in the reals with g of x equals y. So now what I'm going to do is I'm going to use my scratch work, and I'm just going to say let x equal y minus 2 over -3. Okay, so what I have to do is I have to show that this x is a real number, or I have to argue that it's a real number. So I'm going to say then x is a real number because y is a real number. Okay, and then all we did was subtract 2 and divide by 3, so it should still be a real number. So I think that's fine for an argument, that's enough. So x is a real number, and then what you've got to show then is that g of x equals y. Then what you're going to do, you're just going to plug in x to g. g of x equals 2 minus 3 times, okay, now you've got to plug in x, so y minus 2 over negative 3. Okay, so what's going to happen here? So this is your negative 3's are going to cancel out. So this is like negative 3 over negative 3 times y minus 2. I can write it like that. So this is going to cancel out. So this is going to be 2 plus y minus 2 equals, and then your 2 and your negative 2 are also going to cancel. So you're just going to have y. Okay, so yeah, so we've accomplished what we were to show in the proof. We showed there is an element in the domain that produces y as an output. So that's the end of the proof. So once you've done the scratch work, it's not that bad. You just have to plug in what you found. But keep in mind that that scratch work, that is not part of your proof. It's really common in mathematical proofs, actually, when you're reading other people's papers and journal articles and stuff, that someone will just pull an element kind of out of thin air like this. Like they'll just pull something out of nowhere like this, and you're like, where did they get that? Where did that come from? But it just did some scratch work. That's where it comes from. It comes from scratch work. Okay, everybody, I think we'll leave it there for today. So we'll do some more examples about one-to-one and onto and doing proofs and disproofs of those properties on Monday, and then we'll pick up with the other sections that were scheduled for Monday as well. So please send me an email if you're having any difficulties, need any help with your quizzes or with anything else. I'm always happy to hear from you guys, and I'll see you next time.